excited to be here. Really want to thank Grace and Yarko and Sean and all the other folks who made me feel so welcome here, all the organizers here. It's been a pretty good conference so far. Everybody enjoy the tents last night? Was that fun? Yeah. It was pretty fun. I stayed a little bit too late, didn't get home to do the final part of my data science research on the AI community until late, so I stayed up pretty late. But I had so much fun just diving in on some of the stats and data science around what I was going to try to show today. It's a thrill to be here. My name is Travis Oliphant. I've been a part of the Python data science community, machine learning community for a long time. I've been at this for a while, I guess. So I've done a lot of things because of that. When you spend 20 years in an area, you end up leaving a trail. Some of it good, some of it maybe a little embarrassing, but that's one of the things you just do. It's driven me for a long time. I'm very passionate about what we work on, what we do. It's amazing to be able to change the world, one line of code at a time. And we keep being able to do that because there's a lot of needs and the needs keep growing. It's been really fascinating over the past 20 years to watch. So I've been working in science and data science for a long, long time. Didn't call it that back then. We would call it STEM, we'd call it analytical computing, scientific software development. I'll talk a little bit about where I come from. These are just some of the things I've done in the past. So you may know me for NumPy, you may know me for SciPy, you may know me for Anaconda, might know me for NumFOCUS. I was a director of the Python Software Foundation. Know a lot of the folks around. Recently, some people ask about what I'm doing now. So I recently started another startup. It's called Quansight. Basically, it's continuing the tradition of Continuum, which I founded 6 years ago, and Continuum gave rise to Anaconda. We think of it as our first spin out. So some of the founding folks who started Continuum with me have started Quansight, where we're going to try to find other companies to spin out and work with other great entrepreneurs and other great talented people and help really keep moving and taking all the opportunities around data insight to build other great companies. So very quickly, we grow talent, we build technology, we discover products. So I'd like to say we discovered Anaconda, because it's very true. When we started Continuum, we didn't know what we would be building. We had some ideas around distributing NumPy, making scalable pandas, making visualization in the web, and we worked on all those things. And then kind of as we started to do the work, we saw the biggest demand was just installation. And so we ended up writing a package manager in order to solve the fundamental problem of installation across platforms, and not just across Python, but across any language. And so Conda distributes R, distributes Python, I can distribute Julia, I can distribute Node. Anything can be distributed with Conda, and so we use that. That was kind of the discovery phase, and we found that there was a commercial opportunity to help companies with their deployment and installation stories. Those opportunities exist everywhere. And there were several products that we found as well. So we train open source, we train data scientists, we work on open source projects. I'll talk about that a little more. One of the things I'll talk about today is some of the initiatives we're trying to pursue in Quansight labs, where we do open source development. And then we do general services. That's how we keep the lights on. We do work for hire. One of the things I'm super excited about is we've come across an approach to helping companies manage open source, and by so doing, help sustain the open source development. Call it our sustainable open source subscription. Companies can basically come to us and prioritize their needs in the open source space. After decades of working with companies, I've found that a lot of people will spend millions of dollars on internal budgets, millions of dollars in internal software, and effectively do the same thing that open source group is doing. And wasting a lot of their time, and sometimes it works. Sometimes they can actually succeed in producing something that's useful, but a lot of times it doesn't, and the open source project actually goes past them, and they just wasted that money. So we actually help companies identify where in open source they can prioritize their needs and get their work done and often save millions of dollars by doing so. So that's one of the things we do is help people prioritize their needs in the open source. We help people hire from the community. One of the best ways to connect with open source advocates is actually to do something. Go out and sponsor a project, connect with people who are wanting to build something in the world. And then we offer support and services. So it's a new initiative, something we're promoting. I like to kind of help people be aware of it wherever I go. Now today, though, I'm here to talk about AI and ML. In particular in Python, the state, and how am I going to talk about all of this? Definitely I will give a caution. This is a very rapidly evolving field, and there's a lot of material. So despite the fact that I've been doing data science effectively, doing statistical signal processing, I used to teach at university. I used to teach electromagnetism and signals and systems and probability theory, kind of the fundamentals behind machine learning and data science. exactly the technology that's come out over the past couple of years is phenomenal. It's amazing what's in your fingertips, what you can do now with just a few lines of code. And not just one approach, there's like 20 approaches. And we'll talk about some of that today and maybe some things that we can start to do. But I like this diagram because it kind of, it gets to the heart of why we're doing this. Like, we're doing machine learning usually to come up with better decisions and take better actions. Actions that people will appreciate, actions that'll help us do better, actions that'll help the world. And it starts with, understanding the world. We really want, in models, the key part of machine learning is really that pink section. We have better models. That's the idea. Maybe we have better nonlinear models. Most people, when they come to machine learning, either are a little intimidated, inappropriately intimidated, or they have too high expectations. It's kind of one of the two, typically, in the machine learning world today. There's a lot of enthusiasm about what's possible with machine learning, and I'm very stoked about all of that, because it's definitely possible, some amazing things. But at the heart, we're effectively, today, we're doing better curve fitting, right? We're able to build better black boxes that match the world, that match the world. But it's not mathematically too dissimilar from the linear regression we've been doing for years. Not mathematically different. Fortunately, it's qualitatively different because we have better fitting, better models. Things that actually, the world is not linear. The world is complex and has all kinds of relationships. And if you can form a relationship between two things, you can have a mapping between the thing I can measure and the thing I want to predict or the thing I want to understand. No matter how nonlinear it is, if I have enough data, I can create it. And that's kind of the big deal. And why AI is everywhere. There's a few popular things that have occurred over the past little while. Everybody's doing it. And that's one of the reasons that's driven so much enthusiasm, interest in Python, is they've all woken up and they've realized, oh, the whole scientific community is over here in Python, well, we'll just jump in as well. And it's a bit, helter-skelter in some senses. You wake up after 2 years and you realize, man, there's a whole bunch of people have joined up here, which is awesome. And the ideas are kind of scattered a little bit. We're kind of in that phase of just of rapid evolution of ideas, and there'll be some consolidation that occurs over the next coming couple of years. But a number of amazing applications are happening. So I got my training at the Mayo Clinic. Is where I did my. It's where I got into software. It's where I started the SciPy project, as I'll talk a little bit about. I've always been fascinated by medicine and the application of machine learning and data science to medicine. Back even then, long time ago, when I was a PhD student at the Mayo Clinic, the radiologists were all worried. They were saying, oh, we're going to be replaced by the computers. I was in biomedical imaging. We were doing segmentation algorithms, and I did MRI and ultrasound research. And at the time, I knew that now we're a ways from that. One, because computers are still hard to program, they take a long time, and the software we produce is incrementally useful, but not really going to be able to put in front of somebody. Finally, with the nonlinear models and the ability to train them at scale, we are starting to see applications where we're not going to replace radiologists, dermatologists, but we are going to be able to help them, maybe make them more effective, maybe help change the screening parameters so you don't have to have a highly trained physician in front of every image. You can actually put a computer in front of a lot of images and then put the error rate so that it's very low, and then just flag images, and then have the human experts look at just the flagged images. And there's an example of a neural network, and the group was enthusiastic about the success of ImageNet, and they said, let's train a bunch of dermatology images, images of skin cancer and not skin cancer, and train a machine to see if it can recognize just from your phone whether your little growth on your skin is benign or malignant. And they were able to actually match dermatologists. Dermatologists aren't perfect on this either, but the machine was actually able to match trained dermatologists. Now, it took a lot of labeled images, right? That's some of the hidden secret behind some of these amazing success stories, is it doesn't just happen overnight. You running your algorithm on a bunch of data isn't gonna just necessarily, there's a lot of work. There's a lot of hard work. Labeling, discovering, and that's kind of the effort that's involved. But the promises are real, and there's a lot of popularity. Now, as the success in AI has been happening, Python's been growing. I think there's a causation here. I think there is definitely a correlation, but I think it's also one of the reasons interest in Python is growing is because of AI and ML. Just by the raise of hands, how many people have been using Python for more than 5 years? Just raise your hand. Okay, pretty good. How about more than 10 years? Raise your hand. Fewer. All right, how about less than 5 years? Okay, awesome. It'd be awesome to get like a little bit of information about what brought you to Python. And typically, my answers when I talk to people in the past are either it's because of easy data wrangling, there's the pandas story, or there's the scikit-learn story, which is now the TensorFlow, kind of grown up to the TensorFlow story, or the PyTorch story, or the rest. If you look deeper into these data, so what I'm showing here is a plot of Stack Overflow questions. And you can't see it very well, but on the left, you see Python is the curve that's growing up and to the right. And then the other curves are other languages, C++, PHP, C#, Java, JavaScript. They're holding pretty steady from the years 2012 to 2018. But Python is rapidly growing, and we've seen that. And then if you look deeper into the data, you find that it's not just general Python. It's not Django, actually, questions that are growing. It's actually questions about the stack, the PyData stack, as I like to call it, or the NumFOCUS stack, as I like to call it. It's pandas, it's NumPy, it's matplotlib. It's these tools that are used to solve some of the hardest problems in the world. And it's very exciting to be a part of it. So I ran this search because I don't know if you've heard, but Python is now the most popular language in the world. So others might say, and when I've heard that in the past, okay, it's peak Python, so we only have downward to go from here. And that is definitely true. There's some challenges that come with being popular. There's challenges that come with being a lot of people wanting to come to your language. It feels like we've been kind of having some fun, my friends and I, in the scientific space. And now we've been, as I say, we've been farming the back 40. Right? We've been kind of growing our crops, doing some manual labor, having the team with the horses pulling the plow. And now kind of big ag has moved in. We've got enormous tracts of land being filled by larger organizations and larger teams that are producing some amazing tools. And that changes the dynamics quite a bit, and I think that's still evolving. How does that work? How does that make sense? We'll talk a little bit about that. So this is exciting to see, though, and it's only been this past year, and I believe because of the success of the scientific tools around Python that has driven this popularity, especially recently. I'm super excited because I started Anaconda, the company Anaconda, 6 years ago. And one of the reasons was to bring scale to NumPy and pandas. Because basically I was observing that the world was going a little crazy, I thought, because everyone was saying, oh, Hadoop, everyone thinks it's gonna be on Spark, that's gonna be maybe the future. And here I am, a guy who's pulled Fortran routines and fast, very algorithmically fast routines into the modern world through Python by writing SciPy. And I'm just looking at going, the JVM will never solve my needs in that regards. We fought this battle in the 90s when everybody said, hey, analytics are gonna be in the JVM. And resoundingly, the scientific community said, no, it's not fast enough, it's not flexible enough, the JVM doesn't give us the power we need from our computers. And so it was ironic that I thought in 2014, 2015, there was this energy. It's almost like the revenge of the 40-year-old executives, who bet their career on Java, and now they're thinking, thank goodness I could bring it back to analytics. Fortunately, that was a short-lived little scare because a lot of people were pushing Hadoop and Spark, and I literally heard 3 years ago that I would talk and say, hey, there's other engines, there's ways to calculate on your data, to do machine learning, you gotta do a little bit more. And I would have literally people come and say, well, but it's all gonna be on Spark, so why did I just get behind it? Why are you counterculture? So I sighed, right, and kept moving because if you know something's right, then keep getting more data because you're never perfectly right. I'm a big fan of getting more data, keeping yourself open to new ideas. And I would keep digging. I would keep giving clear answers as to my concerns about the JVM being the answer for all analytics. Eventually, fortunately, TensorFlow, Torch, these folks kind of made my argument for me. And so it's been awesome to see that happen, basically, because now the whole narrative has changed. In most organizations, they realize, oh no, yeah, just throwing my data into a big disk, big cloud, big data lake, and then hoping Spark will solve all my problems is not going to work. Spark's a nice tool. It's a part of a family of tools, but I've got to keep open to a large set of tools. And now, fortunately, the cloud native movement is merging, which I love. If everyone says to you Hadoop, just respond to them cloud native, and that'll help you get past some of the negative energy that's been in the world about how to actually make Python work in real world situations. So it's exciting, actually. It's a wonderful time. And I think we really have our friends at all those hardworking TensorFlow and Torch and MXNet people to thank for that trend, that change. I'm super excited by it. This slide I borrowed from Jake and then modified it a little bit. Jake's a good friend of mine from the University of Washington. Jake Vanderplas, we've been associated in the community for a while, and he's been a contributor to SciPy and scikit-learn especially. But this shows kind of the stack that when I think about kind of the scientific stack of Python. The reason machine learning is so popular in Python is because of all these tools. It's not because, Python's a great language, it really is. Has a lot of features. Those features brought a community of scientists to it back starting in 2001, and really before that. And that work of all those folks in that community created quite an ecosystem to where there's enormous numbers of tools. And so come 2015, you're showing up and saying, here, I've got a bunch of machine learning tools. How do I expose them to people? And you look around and say, everybody's in Python. All the people that want to get excited about this are using Python. So that's why Python became the choice for TensorFlow, Torch, Chainer, MXNet, CNTK, and several other machine learning libraries that seem to kind of not cooperate with each other and just build all at once, the same thing, essentially. I love competition. I actually love diversity. I also love standards, and I love people spending time on innovating, not spending time on things that are already done. So you'll hear kind of that theme show up over and over as I talk about the state of the data analysis machine learning world. I put up this timeline so we can kind of get a sense of how this has been evolving. Python started in 1991. 2001 is when SciPy came out, and I started working on SciPy before that, but it came out in 2001, 17 years ago, a long time ago. NumPy came after that. So SciPy was my first love, and that led me to do the work to write NumPy because I loved SciPy and wanted it to survive. But SciPy was actually a distribution of Python masquerading as a library. There's a lot of things it was trying to do, reminiscent of some of the other big packages I see today. Like some people are trying to do all of it. And it can be really challenging to ship that, to maintain it. It's fun at first. You get a lot of stuff out there in the world and you can kind of be, oh, I'm in charge of all this great stuff. And then long term, it's like, well, we have communities that have to maintain this, and how do we do this? And people can't coordinate at scale across thousands of people. You have to have APIs, you have community growth. And that's another talk I can give about how do you actually grow organically communities in a way that's sustainable. So this has been going on for a while. Scikit-learn, huge deal. Scikit-learn actually came from the learnings of SciPy. We said, this is too big, we got to break it up. And so there's a lot of good people who worked hard to create the scikits. Right? The scikit concept came out of the realization that we had to break SciPy up because it was too big to maintain for a group of driven, passionate folks. Scikit-learn, scikit-image. Scikit-learn is the most popular scikit that's emerged, and came out in 2010. Then pandas came out in 2011. Pandas was basically data frames, and we need to be able to manipulate data more easily than just having data structures that are a little harder to use. And then Jupyter, the phenom of Jupyter, which built on IPython, which started 2001 as well. And Jupyter kind of was the next evolution of that effort, the notebook, the interface, the generalization of multiple languages. That was the state of the world in 2014. 2015, significant year, because in that year, all of a sudden you see Torch, you see Chainer, you see MXNet, they all start. Now, we don't see them. You and I kind of basking in our data science worlds don't necessarily notice that's going on. We didn't really notice that until about 2017, late 2016, early 2017. And all of a sudden it felt like it exploded on the world. And we had all these tools, and I've only listed 4 of them here. Torch, Chainer, MXNet, and TensorFlow. All right, how many users of some of these libraries do we have? How many folks are users of TensorFlow? Okay, raise them high, okay. All right, how about Torch, PyTorch? Okay, about the same percentages I'm gonna show here in a bit. Anybody use MXNet? All right, there we go. Yeah, that's great. Actually, MXNet's a beautiful library. It's, we can go into detail of some of the pros and cons, but it's actually well done. And what about Chainer? Anybody heard of Chainer? Any Japanese in the room? Actually, Chainer is the #2 machine learning language in Japanese. It's a phenomenal tool, actually. Toyota purchased a big stake in Preferred Networks, and they use it for a bunch of stuff. A lot of the tutorial materials in Japanese, but all the documentation's in English, and it's available for free. It's very easy to get started with, but it's not as well known. So we've had this explosion of machine learning frameworks and libraries. You've got, XGBoost isn't deep learning, but it's a nice machine learning gradient boosting technique. MXNet, Keras, kind of merged with TensorFlow, Torch, dlib, Dynet, Theano, Paddle, CNTK, NVM, TVM, Caffe2. It's enough to be kind of daunting. You're looking at that going, okay, what is this? Which should I use? Well, a lot of people have kind of done the default. We're in that phase of kind of the market spirits. I think Alan Bernanke and other people in the Federal Reserve have called when people just kind of follow each other. we're that sheep-like mentality phase where everyone goes, oh, Google did something, let's all do it. And TensorFlow is dominating it's sort of they were one of the first to market, and there's a bunch of people doing it. There's a lot of sort of better tools, I think, emerging, and TensorFlow is fixing some of the tools they put out in response to these better tools that are emerging. Better and easier to use, easier user interfaces, more Pythonic. When you first come to TensorFlow, it can be a little daunting, actually. If you're a Python user and you show up with a TensorFlow API, it looks sadly like I've seen a lot of Python APIs in organizations where people haven't tried to embrace Python for its strengths, but tried to see it as just a simple imperative language, and I'm going to translate my Java code to Python syntax. And that's kind of the way some of these tools look at first glance, until you, and then you can definitely tell when somebody's had a more experience with Python. Now, machine learning, lots of talks on this, and you can go into detail about it. This is a simple diagram, just simply showing kind of the complexity that can show up in these models, right? I talk about machine learning, oh, it's just like curve fitting, and well, formally at a distance it is, but it's a lot more complicated. You don't just have two parameters you're estimating like in a linear regression. You have maybe millions of parameters you're estimating. You're estimating the weights, you're estimating the biases. You got a little bit of nonlinearity in there. It's really interesting actually that with just that little bit of nonlinearity each of the nodes, you can construct a generalized nonlinear function that seems to match a lot of real world situations. And of course, there's all kinds of details like convolutional pools, so I don't have infinitely connected sets. I do convolutions up front. I can do recurrent neural networks. I have LSTM nodes. Like, there's a lot of detail that's showing up in the literature, and it's amazing the acceleration of that. There's a lot of really good work going on. So it can be a little daunting, but I think at a high level, you can basically see this neural net, this ML framework, this ML story is I'm estimating parameters of a complicated model. And I can kind of mix, and I've got tools that let me mix and match the components to build a very complicated model relatively easily, and then a system to train those weights and estimate the parameters of that model so I can fit data. And that's the training step. And then once I've trained it, then I can use that model pretty quickly to produce inference or to produce estimates of new data. And that's kind of the whole story. And it's a story we called it estimation theory when I taught at university. And it's the same statistical information, concepts are there, but it's a lot of computes going on. A lot of parameters are being estimated, and it's pretty impressive. Any ML training library needs some of these features. You know, for training, you gotta have the ability to create chains of functions of n-dimensional arrays. Now, though they've been called tensors now in the world, and that word has escaped and it's out in the wild, now they're gonna be called tensors. As a mathematician, I'm a little bit embarrassed by that term because it's the same thing that, you know, an array, two-dimensional array is not a matrix, and just an n-dimensional array is not a tensor. But that's okay. Well, I'll probably use the word tensor, even though I'll hold my breath a little bit, hold my tongue. You have to be able to create these chains of functions on these tensors, right? And that's basically what you've been doing in SciPy or in scikit-learn for a long time. Building chains of functions of n-dimensional arrays is the whole point of having a NumPy and having a SciPy. It lets you do that. You need to be able to derive the derivative of the loss function quickly. So you have to have a loss function, have some loss functions available, things like minimum mean squared, cross entropy. These are kind of loss functions, and I need to be able to differentiate them well. In the past, we do that by hand, and pretty tedious. If you can do it automatically, you can use better optimizers with gradients. So you need optimization libraries, cross-validation methods. And then because what you're doing is, when you're training, you're computing these these chains of functions on n-dimensional arrays over and over and over again. And so to do that, maybe thousands, hundreds of thousands, millions of times. So you want to do that in parallel as fast as you can. And so you kind of need the ability to do this on modern hardware, on GPUs and in highly parallel environments. So you need that. Basically, all these tools to do machine learning have been in SciPy, NumPy, PyData ecosystem, and scikit-learn for at least 10 years. However, in red, the ability to do derivatives easily, and the ability to run on GPUs and FPGAs and other modern hardware, not so easy, right? That's where a lot of the innovation was needed. Now they're available now in things like CuPy, that brings a NumPy array to GPUs. Things like AutoGrad, lets you do differentiation on NumPy arrays. But those were kind of missing pieces. And that's kind of what the machine learning frameworks are bringing to the Python ecosystem of the analysis, the data science, the analysis ecosystem. For inference, it's actually less you need. You don't need quite as much. You just need to be able to create those chains and then execute them on perhaps different hardware, multiple kinds of hardware, perhaps FPGAs, perhaps IoT devices, perhaps you want your library to run on mobile phones. You want it kind of distributed everywhere, maybe even the web. So most libraries, kind of fundamentally, in 2015, when a bunch of people came to the space, there was an existing set of tools that were available to use, and most libraries, they needed some features. They needed some things added. They needed some GPU support. They needed some ability to do differentiation. And most libraries decided to re-implement, basically, a whole lot of stuff. As opposed to sort of improve the ecosystem, they just re-implemented a whole kind of silo on their own. Chainer is one exception. Chainer did it kind of more in a, what I would consider kind of taking the community and then trying to move the community forward. Now there's reasons for that. Really good reasons, actually. You might need the stack to work with other languages. Fundamentally, your Python is just one of a bunch of languages. So what you need is effectively an analysis stack, an array analysis stack that works in C++ and Go and Node. And so that's a reasonable reason. You have legacy code to integrate with. A lot of folks, like PyTorch, came from the Lua community. They had Torch, and there was a Lua community that had to work. 5 minutes. Next talk is 10:15, right? Oh, I see. Oh, okay. Great. Well, those who don't want to keep a break can stay with me. Needed only a subset of functionality in NumPy and SciPy to build ML. Or they lack familiarity with the NumPy SciPy ecosystem. I think that's a big one. With so many new people, there's a lot of new people, and they just really don't know how to interact. And maybe the NumPy and SciPy communities, the Pandas communities, were not as open and eager and easy and accessible. Definitely a lot of reasons. So, state of the world, a bunch of folks come to the world and kind of build these ecosystems. And so what's the status? These are just some basic summary stats you can see. Primary sponsor, the number of stars, forks, contributors, releases, and the number of participants, which I'll talk about where did I get that number a little bit later. So these are, obviously TensorFlow is this dominant one. It's huge, right? It's just enormous in terms of a project. It's only React, and projects like that have more stars and more participation. A lot of people around TensorFlow. Torch, MXNet, kind of very, very also useful. If you look at NumPy, for example, NumPy as a project is about like the paddle, stars, forks, with more contributors, with the number of PyTorch contributors. That's kind of to give you a little bit of grounding. And then Theano, which had been there for a long time, and it has basically been deprecated by the group. Now it'll be continued by community folks, is now there. If you haven't checked out Chainer, check out Chainer. A lot of people love it, and it's a very sort of community-friendly tool that builds on top of NumPy. It uses CuPy, uses all the tools that you know and love, and yet it lets you do machine learning at scale. It's a deep learning framework. It does all the things, design a network, lets you train and evaluate it, lots of features, works on GPUs. A lot of add-on packages. In fact, ChainerMN is a multi-node scalable version of Chainer that lets you train across multiple GPUs. And in fact, it's the fastest way to train on multiple GPUs. Chainer beats MXNet, CNTK, and TensorFlow for training speed, at least in 2017. So the world is changing rapidly, so perhaps this may change again. So I wanted to explore the communities around these products a little bit better. So there's this SQL code you can write, and ended up spending a bit of time trying to make sure this worked. And I basically probed a bunch of different projects, Theano, CNTK, TensorFlow, Paddle, looked at the communities around them, trying to come up with a measure of the health, the strength, the participation of these communities. And I was looking at basically comments, pull requests, review comments, releases, and then closed, renamed, and labeled issues. And then I put a score, 1 for a comment, a 5 for a pull request, a review comment's a 5, release is a 50, it's a lot of effort to do a release, and then a closed, renamed, labeled issue of 5. So kind of score that, come up with a weighted score for each participant in the community, and use that to kind of look at these communities and see if we can't, very, very exploratory. Good community health metrics is not something, if anybody knows of better ways to do this, I've been thinking about this for a little while, but came up with kind of then I translated this, turned it into effectively these scores. We're gonna look at the cumulative distribution function of these scores. Treat it as a random variable, and then treat it and then look to see what the distribution looks like. And this is a raw score, so it's against this number, this weighted participation number, right? And you look at the different PyTorch, for example, really a lot of participation. And you kind of see that the participation, the narrower it is, the fewer people are participating. You might have a lot of participation, but the fewer people are doing it. And the broader it is, the more people are participating. If we scale this, so it just maxes out at 1, so your percent of participation, and you can look at these organizations, you kind of see something about the community. I'm not quite sure what, but you do see something about the community that's different. Maybe, I tend to think that a really healthy, lots of people involved in the community would probably have a more linear curve. You look and see the number of people participating is kind of more spread throughout the organization versus kind of a one-sided community where there's a lot of people, only kind of a few people participating. Maybe it's not quite as big, not quite as robust. Again, very unscientific, but it gives you a perspective. This is an example of kind of data science, a lot of work, not sure if it says something, right? You can definitely do it with numbers. You can do a lot of amazing things, show some numbers, and then try to hope to show something. But at least it does show some comparisons, and you can look at this over time and see maybe what's changing. So don't have a lot of time, so I'm gonna have to go fairly quickly. But I wanted to kind of get to a point about where NumPy, SciPy came from and kind of where do we go from here. You know, we have all this wonderful new tools, we have all this wonderful contributions from large companies, large organizations. How do we use this to integrate, to continue the momentum forward so that we get more and more great tools out there? So I got started because I was interested in medical imaging. I wanted to take ideas and be able to take measurements from the body and then translate that to decisions and actions in medicine. That led to Python. That led to a lot of work writing code. I ended up writing a bunch of code from early 1998, and that code that I wrote then continued in 2001. 99, I put off my graduate program for a year and basically worked on open source code. Familiar pattern, lots of people have done that since. In 2001, I got together with a few folks and brought tools together and made SciPy. Then I saw as SciPy emerged, there's this other array library, NumArray, and NumArray there were other packages being built for NumArray, packages built for numeric, packages built for NumArray, and that was really bothersome because I didn't like the fact there were these stacks of libraries that I wanted to use that I couldn't unless I copied all my data over to another array object. You know, it just meant that it was harder to reuse code. I wanted to break down those barriers. That's why I spent time writing NumPy. So really in 2005, 2006, I brought numeric NumPy together to create a single array object that the community could use and build on top of and share and communicate with and coordinate on. Mission accomplished. Really excited about that. In fact, I didn't get tenure at my academic career because I spent time doing this, right? Super excited. Large community effort now. The success of NumPy is because of all the wonderful people that have jumped in and helped continue to make it happen. There's lots of contributors making SciPy and NumPy happen. Fast forward 10 years, and now we've got array objects everywhere. Such a good idea to do array computing. I love array-oriented computing. Now we've got them everywhere. And so we're kind of now back in a divided community again. So it's a little bit, can be a little bit daunting. You see all this work to try to unify the community. The success breeds lots of diversity. And so that can be exciting. It's actually a new opportunity, I think, to kind of help bring kind of like this. Let's see if we can't bring interfaces together. Maybe not implementations, let's bring interfaces together so that people can start to work together again. We are starting to see this breaking of communities, this siloization of communities, even in Python itself. You have packages being built on Torch. You know, reusable libraries only on Torch. You have reusable libraries only on TensorFlow, and there's sort of this separations occurring. So there are some unification efforts, although they're not as popular as just the feature building efforts. One example is Gluon. Gluon's an effort, and it's kind of like Keras and Gluon. If you take nothing else from this talk and you use machine learning libraries, I would say use Keras or Gluon. Don't use the low-level library implementations. Use the high-level ones, and then you'll be able to transport that in the future when things change. You won't be so stuck with one implementation or another. But there are other things like Sonnet that are kind of like Gluon, but only for TensorFlow. So, and you know, TensorFlow is not necessarily participating in some of these efforts because they don't need to, in some sense. They're kind of the dominant, and so they don't necessarily need to. But Gluon gives you an easier way to write code, makes it a little simpler, and you can build very complicated neural networks very quickly. Other unification efforts, Onyx. Onyx is an approach to train the model, then write to a common format, and then you can apply that format to other platforms. It's a participation between Microsoft, Facebook, Amazon, so CNTK, Torch, MXNet, and as others as well. There's a whole lot of folks participating in this effort as well. Onyx is something I'm very excited about. I think it'll definitely help so that you train in one area and then you can deploy anywhere, and that doesn't matter so much which one you use to train it with. NNVM, TVM, an ambitious plan at University of Washington. Smart folks up there. They brought us a lot of things that are really cool. This is a very exciting architecture they put together, but it's early stages still. It's about kind of you can almost think of like an IR for machine learning at the low level that everybody can target. And that'd be great to see something like that emerge. There's another solution, or sort of a start of a solution. That really, when we did NumPy, we didn't fix it once, we fixed it twice. We solved the problem of bringing the arrays together, but we also introduced an array interface, or the beginnings of one. We introduced what's called the buffer protocol. This allows any object out there in Python land to share its data with any other object through a very simple interface mechanism, the buffer protocol. If you haven't heard of the buffer protocol and you know anybody working on TensorFlow, Torch, MXNet, go teach them about the buffer protocol. It would be awesome if they actually supported it. because it would help the siloization that occurs, because it means you could basically build an array in anything and then share it with your neighbor, and they can reuse it. And it's just a simple API conversation. It's not copying a bunch of gigabytes of data. So it allows all array objects in Python to coordinate. Now, there's some limitations to it, and there's some improvements that need to be made to this array interface, and I think that's where the opportunity exists. The opportunity exists to actually take that buffer protocol, that array interface concept, go back, take the learning we've maintained for 15 years and go back and build an array interface that can actually support all the implementations of arrays we have now, and ensure that the stacks we build on all follow the common API, so that we don't have the siloization, so we can reuse each other's work, so we can share and kind of more standardize around this awesome opportunity of machine learning and what I call differentiable array computing in the modern world. And if we do that, then we'll not limit our progress. We'll sort of not just have this plateau of great use that we then stop being able to coordinate. How do we continue to coordinate together? It's the same energy that's been happening. We've started this work at Quansight Labs. Quansight Labs is a part of the Quansight effort where it's a R&D open source research lab that we're working on together. Super excited by the opportunity. Thanks for spending time with me, and thanks for hearing me out, and I'm happy to answer questions later.